Hello class, and welcome to this video lecture on collision theory, part 1. Okay, so let's talk a little bit about some of the points of collision theory. In order for a reaction to occur, the reacting species must collide. Collisions are necessary, but not sufficient for reactions to occur. A collision that results in a reaction is called a fruitful or an effective collision. Okay, so there has to be enough energy for a reaction to occur. The reacting species need enough energy in order for a chemical reaction to take place. Activation energy is the minimum amount of energy necessary for a chemical reaction to occur. And we denote the activation energy with this symbol right here, E sub A. Okay, so that's the minimum amount of energy needed for a chemical reaction to occur. When the reacting species collide, kinetic energy, or energy of motion, is converted to potential energy. And it's the potential energy that can break bonds. As you may know, energy can be converted from one form to another. And there are several different types of energies that you may have encountered before. Kinetic energy is energy of motion. Potential energy is stored energy, and there are many different types of stored energy. Radiant energy, we typically call that light. There's electrical energy, nuclear energy, vibrational energy. So sometimes molecules, they're not moving around, but they're vibrating. And rotational energy, molecules can rotate. So these are just a few of the different types of energy that we can encounter. Okay, so to get into a little bit more detail about collision theory, let's take this kind of hypothetical reaction, A plus BC, to give AB plus C as products. Not only must A and BC have enough energy, but they must also be oriented properly in order for a reaction to occur. Okay, so for example, if we have A moving in this direction and we have BC moving in this direction, and this is to kind of signify a collision between both of those, a reaction will result if there is enough energy. Okay. If you look at this overall reaction here, you can see that in order to get from reactants to products, this BC bond has to be broken and a new bond has to form between A and B. So a bond between A and B forms at the same time that the bond between B and C is broken. So if the molecules are oriented in this fashion and they are coming towards each other with enough energy, a reaction can result. Okay, so what if we just kind of inverted this? In other words, if this molecule was turned around and this molecule was headed towards this molecule here, however, it was oriented differently, okay? And there's a collision between both of them, okay? We're not going to get a chemical reaction. Even if there's quite a bit of energy present, because AC is not a product. Okay, we don't want a bond to form between A and C. AC is not a product. We want a bond to form between A and B. So when these molecules collide, the B has to be facing towards the A in order for a reaction to occur. So orientation is something that's pretty important. Okay, so let's look at the energy aspects of reactions. And again, we'll just kind of take this overall kind of general reaction here. We can use what's called a reaction progress curve to show the energy during the course of the chemical reaction. Okay, so in a reaction progress curve, we're kind of showing energy versus the progress of the reaction. And a typical curve might look something like this. Okay, so the reactants start off at some energy. The products are going to end up at another energy, a different energy. Okay, so I'm showing my reactants here, A plus BC. The products over here, AB plus C. Okay, so there's kind of a curve here in going from reactants to products. Okay, now at the very, very top of the curve, really the highest energy, that position in the reaction is called the transition state. Okay, and what we have at the transition state is an instance where the bond between B and C is being broken. That's shown with this dashed line here. At the same time that a bond between A and B is formed. So in the transition state, there is bond breaking and bond making or bond formation occurring at the same time. And this species here, we call it the activated complex. It is the species present at the transition state. Okay, so in terms of the terminology, at the beginning of the reaction, we have the reactants, which are shown here. At the end of the reaction, we have the products, which are shown here. And at the transition state of the reaction, we have what's called the activated complex. Okay, very, very high energy. This is very unstable. Remember that the higher in energy something is, the less stable it is. We can't stop this reaction at this point. I can't grab this activated complex and stick it in a bottle. Okay, it's very, very unstable. That is the activated complex, which is present at the transition state. Okay, so let's look at some details here about this curve here. Okay, so you can think of this, class. This is kind of a very simplistic example, but imagine, if you will, imagine that this is an actual hill. Okay, and you are standing here, and on the other side of the hill, maybe your friend is standing over here. Okay, and you're standing here, and you've got a ball, and you're trying to roll the ball over the hill. Okay, to your friend who's standing over here. So now you can get the ball, and you can roll it. If the ball doesn't have enough energy, it's just going to roll right back to you. Okay, so you can keep trying to roll this ball. If there's not enough energy there, the ball's just going to roll back. However, if there is enough energy, you'll be able to get this ball over the hill and down to your friend, okay, who's standing down here. Okay, so there is a barrier. There is some amount of energy that must be overcome in order for the reaction to occur. So if we were to consider the amount of energy it takes to get from the reactants to the very top of the hill, we call that the activation energy. Okay, remember, we define the activation energy as the minimum amount of energy necessary for a reaction to occur. Okay, so that would be the activation energy. Okay, so imagine class, that you're standing here, you roll the ball over the hill, okay, and so to your friend who's standing down here. Now, in theory, your friend could roll the ball back to you. It's going to take a lot more energy to do that, okay? There's a much larger energy barrier to get the ball over the hill, okay? But in theory, it could happen, okay? So if we consider the amount of energy it takes for the reaction to go in the backward direction, okay, that amount of energy would be the activation energy. And so what I've shown here with this blue arrow, again, this is in theory, this would be the activation energy for the backward reaction, okay, and going from products to reactants. So since we can really have two activation energies, the activation energy for this reaction, the activation energy for the backward reaction, we're going to be a little more specific here and say this red arrow indicates the activation energy for the forward reaction, whereas this blue arrow here indicates the activation energy for the backward reaction. Okay. Now, you might recall from Chemistry 1, there is a thermodynamic quantity called the enthalpy change, which we indicate with delta H. Okay? Mathematically, the enthalpy change can be calculated if we take the activation energy for the forward reaction and subtract the activation energy for the backward or the reverse reaction. Okay. Now, that enthalpy change would be indicated right here. The amount of energy right here, this green arrow here indicates the enthalpy change. Now, you might notice here that we're talking energy here, okay? So when we talk about energy units, you might recall from Chemistry 1, there are a couple of different energy units that we can use. Your textbook kind of emphasizes the joule, indicated by capital J. That's an SI unit. The calorie is an older metric unit. That's indicated by a CAL, cal. And of course, you can use all of the SI or metric prefixes that you remember: kilojoules, kilocalories, megajoules, gigajoules. Okay. Now you're not going to need to memorize this, but this is the conversion factor in going from joules to calories. If you ever have to convert, between these, 4.184 joules is equal to 1 calorie. Okay, now, if you have a negative value for delta H, if the delta H is less than 0, then heat is given off and the reaction is exothermic. We would have a negative value for delta H in this circumstance. Notice if you take the activation energy for the forward reaction minus the activation energy for the backward reaction, for this particular case, the activation energy for the backward reaction is greater than that of the forward reaction. So you're going to end up with a negative delta H in this instance. So if it's ever negative, that's going to be an exothermic reaction. In other words, the products have a lower energy than the reactants. Okay. Now, let's take a slightly different looking curve. Okay. So if the curve looks like this, now what's the difference here? Well, here the reactants have a lower energy than the products. Okay. We still define everything in the same manner as we did earlier, okay? So the amount of energy it takes to get to the top of the hill, so to speak, that's going to be indicated with the red arrow. That's going to be the activation energy of the forward reaction, okay? So here it takes much more energy to get to the top of the hill going in the forward direction than it does going in the backward direction. Okay, so the amount of energy that it takes to get from products to the top of the energy barrier, okay, that's going to be the activation energy for the backward reaction. Okay, so we still define the enthalpy change as the activation energy for the forward reaction minus the activation energy of the backward reaction. Notice here that this is going to be a larger number than this. Okay, so delta H is still going to be the difference between both of those, indicated by this green arrow here. Okay. In this case, we get a positive delta H. Okay, so if delta H is positive, then heat is absorbed and the reaction is endothermic. Okay, so you're either going to have an endothermic reaction or an exothermic reaction. Okay, so in an endothermic reaction, the energy of the products is greater than the energy of the reactants. Okay, so we're going to continue our discussion in another video. We're going to continue our discussion of collision theory. I hope that you have found this to be beneficial.